Welcome. My name is Ed Malthouse. I'm a professor at Northwestern University, and this is the first of a series of roughly 25 videos that I intend to make that will cover time series and forecasting methods. Before I get into this, let me just mention that the textbook that I'm going to be using along with these videos is this one by Rob Heinemann, so Forecasting Principles and Practice. I think it's an excellent book. It's very easy to read, lots of really good examples, and examples in R, the statistical package R that we're going to be using. By the way, I think R is an excellent environment for doing time series models. Rob Heinemann was the person who developed the forecasting library, and I think he did just a really good job on it. I'll just mention another book that I've been reading to go along with this. It's a book by Douglas Montgomery. It's another classic. I like it because it gives a little bit more of the mathematical detail without using kind of advanced mathematics. So that's another book that I like. What I intend to do in this first video is really just establish a lot of definitions. So what is time series analysis and forecasting? What are the issues that go along with it? And what are a lot of the concepts that we're going to need in order to discuss this? All right, so we've been seeing a lot of time series data in the news recently. So I'm making this video during the middle of the pandemic, and so you can't open a newspaper right now without seeing some sort of time series data showing the number of cases today. Okay, so that's one example of a time series. So a time series is just a sequence of measures at roughly equal points in time. I'm going to be denoting these measures over time by little y sub t. So little y sub 1 is going to be the measurement at time 1. So the first day that we've started tracking COVID cases that would be the number of cases on that day. Y2 would be the number of cases on day 2, all the way up through y sub big T. So big T I'm going to be using to indicate the number of observations that I have in my time series. All right. Usually with regression and other stats classes, we use the letter I to index the observations, so the rows, if you will, that we've observed. We don't use I in time series analysis. Instead, we're going to be using the letter little t. Okay, so when I say y sub little t, as I have right here, what that means is, the measure of whatever I'm observing at time little t, which ranges from 1 through big T. One other really fussy point that I'm going to follow, so following a lot of elementary stats books, I'm going to use big Y whenever I mean a random variable. So a random variable indicating this quantity that I'm going to be measuring at time t, versus little y sub t is going to be a realization of that random variable. So a lot of you may not care, and you can kind of ignore that distinction, but I will be following it, trying to follow that throughout the course. Well, what is forecasting? Well, forecasting is about predicting future values of y. Now, one thing to note about this up front, and something that makes it very difficult, is we are extrapolating. Okay, so by definition, we're going beyond the end of the data. Okay, so how many COVID cases will we have tomorrow is an example of a forecasting question. How many cases will there be 1 week from now, 1 month from now, 1 year from now? Those are all forecasting questions, and the fact that it's all outside of the range of my data, so my data spans from period 1 through period big T, the fact that we're trying to make a prediction about something outside the range of data makes this a very difficult question. All right, so what are we going to do? How do we make this forecast? Well, there's a lot of ways that we can make the forecast. One is just using past values of y. So what happened yesterday, what happened the day before, will tell me a lot about what's going to happen tomorrow. Sometimes we will have some decision variables available that we know affect Y. So a great example of this would be the marketing mix. So if you're in some sort of business forecasting situation, the marketing mix consists of, I like to think of it as stuff that you have control over in marketing. So what price are you going to charge? So if Y happens to be the sales of your product next week, the price that you charge is obviously going to affect that. So that is one marketing mix variable. Another one could be the amount of advertising you do. Okay, so the more advertising I do, the more sales I'll have. That would be another marketing mix variable. The distribution, so place is what marketers call it, could affect this. If I change the way I distribute my product, that will also affect Y. So the point is, there are other things that are under my control that could affect Y, and maybe I need to incorporate that in my forecasting model. Not always, but often I do. Another class of information that we have available is knowledge of future events. So these future events, I may not have control over, but I know something about them. So for example, if my Y is beer sales next week or in week T, I might know what the weather forecast is going to be. And so if the weather forecast is going to be warm, maybe people will drink more beer than if it's going to be cold and rainy, because then you don't want to go out and have a picnic. All right, so that could be one example of something that's not under my direct control, but will affect Y. Likewise, if Y were ice cream sales, same situation. Temperature is one example, a policy change. Okay, so if we all of a sudden change certain social distancing policies in a country, that will probably have an effect on the COVID cases that occur in a future time period. Okay, so that's the basic problem of this course, is how do I predict this future quantity based on previous Y values, stuff that's under my control, stuff that's out of my control, but I have a pretty good idea that it's going to happen. So I can say with some certainty what the weather will be like next week. All right. Time series analysis, on the other hand, is I think of it as slightly broader. So there are three main things that I may be doing with a time series analysis. So description, prescription, and prediction. I got those out of order, but you know what I mean. So description just means I want to be able to describe how Y changes over time. So more on that in a minute, but maybe I want to know, is there seasonality? So do I sell more in summer than I do in winter? That would be an example of a descriptive question. Is there a trend? So are COVID cases increasing right now? Are they decreasing? That would be another descriptive question. The second task is prediction, which is really the forecasting part of this. The last one is what I'm going to call prescription or normative tasks, where I'm really trying to make some causal inferences using the time series data as a quasi-experimental design. So an example of a causal inference could be if I shut down the bars in a state, does that cause cases of COVID to decrease? That is a causal inference. I'm saying that my act of shutting down bars has this effect on cases. All right, well, we're going to need different methods to study each of these three types of questions. So description has nothing to do with causality, it's just describing what I see. Prediction is about forecasting the future. Prescription is understanding how some factor affects the Y. Now, there are various models that we're going to be studying. So explanatory models predict Y using predictor variables. So these predictor variables could be things like the marketing mix. They could also be things like temperature. So temperature or policy change would be an explanatory variable. Time series models predict y based on just the previous values. So that's this first line. Mixed models are going to use them both. So what determines the quality of a forecast? Well, first thing that's going to determine the quality of a forecast is how well we understand and can measure the factors that contribute to whatever it is I'm forecasting. So if I'm trying to predict my sales of ice cream, how well do I understand exactly what factors are going to affect the sales of ice cream? So certainly the marketing mix will be one of those. My competitor's marketing mix will also affect that. So how much advertising and what price my competitors are charging will also affect my sales. If I have very little understanding, then I'm not going to be able to make very reliable forecasts of my sales. So something like the stock price of a company next week will be a very difficult thing for us to forecast with reliability. Another factor that will affect this is how much data we have. A lot of situations, you just don't have a lot of data to work with. So back in the beginning of the COVID crisis, there wasn't much data to work with. Maybe you could study previous pandemics in the past and try to make inferences from that. But that's a very different situation than we're in now in summer, where we've observed quite a bit of data on COVID in different cases under different conditions. So there's a lot more to work with. Another factor is the signal-to-noise ratio. So what I mean by this is, so some of what we observe in Y, it will be related to the things we know about. The noise is what I can't model. I don't understand it. So I lump it into this random part. So how big is the stuff that the variance that I can explain versus the variance that I just don't understand? And so high signal to noise ratios means that you can forecast something pretty well. Low signal noise usually means that your predictions are going to be pretty inaccurate. Another big question is how similar will the future be to the past? And so if we could have forecast sales of various products back in January and made predictions for the next 6 months, and of course those predictions would be very wrong because the world has changed, because COVID has happened. Demand for certain products has soared. So grocery delivery services have done very well. Demand for other products have completely plummeted. Okay, so if the future is not like the past, you're gonna have a real hard time forecasting it. And if it's pretty similar, then you'll be able to do pretty well. Finally, sometimes the act of making or publicizing a forecast will actually affect the variables that you're forecasting. So if I'm a large brokerage house forecasting, the future interest rates, or that's probably a bad example, but the future stock price of some stock, and investors follow my forecasts and go buy it. If I say the stock is going to go up in the future, and then a bunch of investors follow my advice and go buy it, the stock price will go up, not because of something else, but it's because of the forecast that I publicized. Okay, so that also makes forecasting extremely difficult. In marketing, which is really what I'm going to be dealing with in this class, that doesn't happen as much. So if I make a forecast for my ice cream product next week, consumers don't know about that, and the stores don't know about that, so it's not going to affect my sales next week in the way that something like a financial market forecast could. All right. There are 4 components of a time series. So the 4 components are trend, seasonal, cyclical, and random. So we're going to call, this is slightly confusing, but it's pretty universal. Big T sub little t is going to tell me what the trend is at time t. So what I mean by a trend is it's some long-term, so long-term is really key here, deterministic pattern. Okay, so if my sales are going up following a line over time, that would be called a linear trend. Likewise, if it's an exponential curve, so that's increasing, that would be a trend. So the key thing about trends is they are long-term. The seasonal component I'm going to call S sub t, big S sub little t. And what I mean by seasonal is some regular or periodic effect. So if we look at something like retail sales are always higher in the fourth quarter around Christmas, always lower in the first and second quarters. That happens on a regular period. So every fourth quarter when Christmas happens, retail sales go up. In January, they tend to go down. Okay, so that's a regular effect. Cyclical effects, which I'm going to call C sub t, are midterm. So they're not long-term, they're midterm, regular, don't say regular, but irregular variations. Okay, so things go up for a while, then they go down for a while. And the key here is they happen at irregular time periods. So this is often tied to something like the business cycle. So if we look at retail sales, while the economy is doing very well, we may have higher sales than we would normally expect using just the trend and the seasonal components. And then when we go into a recession, maybe retail spending drops, or unemployment would be another example of something that would follow the business cycles. All right, so that's the cyclical part. Finally, there's everything else. So that's lumped into what we call the random part. We're going to call that epsilon sub t. Now, let me just mention that it can be difficult to separate the trend and the cyclical parts conceptually. And so sometimes, for example, the Heinemann book refers to this as a cycle trend, where he just combines the two. All right. The terminology is often sloppy. So I just read an article yesterday that said we see an upward trend in daily COVID-19 cases. Okay, what they're really meaning here is that the line is going up right now, and that's kind of a midterm pattern. That's not this long-term deterministic pattern. Okay, so the language gets kind of sloppy between cyclical and trend, and just be aware of that. All right, one other thing to be aware of, so just to kind of describe everything that we're going to have to deal with, is sometimes trends and seasonal effects are going to change over time. So I'll give you some examples of this in a second. Actually, one classical example of a seasonal effect that changes over time that Heinemann talks about is the demand for electricity. So the demand for electricity is fairly seasonal. In summer, we have air conditioners. We use a lot more power. In spring and fall, not so much. Well, that's gotten worse since air conditioners became very common. So prior to air conditioners, the seasonal effects were not as great on the demand for electricity. So when we build a forecasting model, we have to account for the fact that sometimes these things change. So what I'd now like to do is just walk you through a few examples of some time series. We'll get into how I generated these plots in a later video. But this first time series plot shows the yield on 3-month Treasury bills from 1970 up through about 10 years ago. And so what you should notice about this is there are some peaks, and then there are some valleys, and there are peaks and valleys, and these peaks and valleys don't occur at regular intervals. Okay, so sometimes they're right next to each other, sometimes they're over extended periods of time. And this is a classic example of a cyclical time series. So there's cyclical effects where things go up and then they go down, but there's not necessarily a seasonal component. It's not like Treasury bills have a higher yield in every December and lower yield every January. That doesn't happen with this particular time series. Okay, so this is an example of a time series that I would say has only a cyclical component. There's not really a long-term trend. Maybe it looks like it's going down right now, and it's continued to go down as we've hit COVID. I suspect that these interest bill rates, the interest rates are going to go up again to 5%, and if the economy gets, at some point it could even go up as it was in the early 80s to a high rate. Okay, so there's no seasonal, there's no trend component, but there's definitely a cyclical component here. Okay, let's contrast this with, these are quarterly sales for Amazon.com over time. Now, what you should notice here is there is a regular pattern. Okay, so what I'm really seeing here is kind of three lowish figures and then a bump. Three lowish figures and then a bump. And that bump, I think, is Christmas. All right, and so that is an example of a seasonal component. The other thing I see here is an exponential trend. Okay, so there is a general trend that Amazon sales are getting larger, and the slope is actually increasing over time. I think it's going to be exponential. Not sure yet, but that's just eyeballing it. Another thing that you should note about this is that the amplitude of the seasonal effect is getting bigger. Okay, so back here you can see mini bumps. The bumps become much more prominent as basically the mean sales increase. So the amplitude of that effect increases, which is kind of reminiscent of heteroscedasticity in regression. So we're going to have to deal with that when we model this data. All right, so this is going to be a bit of a pain to model unless we do a log transform. We're going to log transform that, and logs are going to make our life easy. But if we had to model this effect that the seasonal amplitude gets bigger each year, we'd need a fairly complicated model. All right. So here's a really famous graph that I've been seeing in the newspaper every day, which is COVID cases by day since the pandemic started. What you're going to notice here is really a seasonal effect. Okay, so the season here is occurring every week. And so what's happening is not as many cases get reported on the weekend. So my understanding is that reporting offices are understaffed on weekends. They have better staff on weekdays. And so, come Saturday or Sunday, you just, so the reporting just doesn't happen as efficiently on weekends. There's a backlog of cases, and so you get a lot more cases being reported in the middle of the week once they've worked through their backlog, and then the cases fall again on weekend. So that's not a real effect. It's not real in that it's not that people tend to get more COVID on weekends than weekdays. Oh, by the way, testing stations are more likely to be open during weekdays than weekends. So it's not that more cases are occurring. It's just that more cases are reported due to any number of factors in our healthcare system. Okay, so we see a strong seasonal component happening at the weekly level. The other thing that I see here is kind of I would describe this as a cyclical pattern where there was a strong increase in cases. The U.S. shut down. These are in the U.S. After a while, things started to decline a bit, then the US opened up again somewhere, depending on the state back here, and then cases grew again. The general trend is upward, and I mean that in kind of a midterm way. Hopefully the cases will decrease again as they have in other countries. Okay, the last example that I want to give is the change in Google stock price over time. So this is how much, did Google's stock price increase or decrease on a given day. And so what I think you'll see here is there's not much of a pattern. There's nothing regular, so there's no seasonal effect. There's no trend. The daily change is just seems to be random. Okay, we're going to have a special name for this. We're going to call this a white noise process, or just a random process. And we're actually going to test for randomness in a subsequent video. All right, so what you should be able to do at this point is identify these 4 types of patterns in different plots. So trends, seasonal, cyclical, and then everything that's left is random. We're going to study some methods that will kind of help us see these later on when we get to the decompositional methods and other models. All right, one more term that we need to introduce at this point is the difference between an additive model and a multiplicative model. So an additive model is where my sales at some time t is some trend plus some seasonal effect plus some error. Okay, so this would be an example of an additive effect. And by the way, I've set the errors to 0 here. There is a linear trend. I rigged it because I made this data. There is a very strong seasonal component where it looks like every 3rd dot is high. Every 3rd dot is high. The others 3 are low. And I omitted any errors. There are no cyclical components. Multiplicative, on the other hand, is where it's a product. Okay, so it's going to be the trend component times the seasonal component times the error component. The error component here is 1. And so this gives rise to a time series where the amplitude increases over time. So it's very reminiscent of what we saw with Amazon's stock price, or the amplitude of the period increases. Now, what we're going to do with these is just log both sides, or take some other transformation. But log is a particularly nice one, because the log of a product is just the sum of the logs using properties of logs. And so by taking logs of both sides of this, we convert the multiplicative model to an additive model. So be able to recognize these features from scatter plots, these time series plots, multiplicative, additive, cyclical, trends, seasonal, that's very important. So finally, what I'd like to do is to give you an overview of what we're going to do in this class and beyond. So one approach that we can follow is regression. So we can do regression, make sure you have a solid grasp of regression. If you don't have that, go watch my other videos where I teach basic regression. Something that's going to be extremely important for us, so don't forget this, is the difference between regression and time series. One of the main differences is going to be the errors. So when you take a basic regression class, you always assume that the errors are independent of one another. One of the big differences that we're going to have to address, and that makes time series difficult, is the fact that the errors can be correlated with each other. So the one y can be correlated with the next y over time. We're going to call that autocorrelation in a minute. And that happens because the errors are correlated. So we can do a lot of things with regression models, But just be aware that the limitation of regression is one of the big limitations is addressing the correlated error problem. So what are we going to do about this? We're going to study some other methods that work. So decomposition methods are going to be one of the early methods that we talk about. We'll talk about those in week 3. Exponential smoothing. So some of the big names to know affiliated with exponential smoothing are exponentially weighted moving averages, so EWMA, and Holt-Winters smoothing is another example of exponential smoothing. So we're going to do decompositions and exponential smoothing in week 3. Another very important method is called ARIMA. So ARIMA, otherwise known as Box-Jenkins, I happen to have the original Box-Jenkins book on my shelf, is a very different approach to handling this, and we're going to cover that in time 4. Week 4. Week 5, we're going to talk about dynamic regression, which is how do we model these correlated errors and include predictive variables and regressions all at the same time. So that'll be probably week 5. We'll see how the videos go. So when do you use these different methods? Time series is a vast field. I'll just kind of point out how vast it is by pointing to the Montgomery book. So the Montgomery book is over 600 pages long, and it's called An Introduction to Time Series. So it takes 600 pages just to give you an introduction. That's how vast the subject is. So descriptive methods, well, we're going to start with this week. Regression tends to be really good for descriptive questions, okay for prediction, pretty good for prescription, especially once we combine them with the ARIMA models to take care of the problems with the errors. Decomposition methods, on the other hand, really good for description. I really wouldn't recommend them for prediction. Don't use them for prescription. Exponential smoothing models are going to be pretty good for description, really good for prediction. You're not going to use them for prescription. ARIMA models, kind of similar to exponential smoothing, I say they're just okay for description. I find them a bit more difficult to interpret, the parameters. That's my opinion on them than the exponential smoothing methods, but they're among the best for prediction. Combining regression with ARIMA gets us to these dynamic regression models, and those are going to be pretty good for all of them. All right, I'll just close with references that you might want to know about. So every business stats book on the planet will have at least one chapter on time series, and they usually do a very good job of covering it. It's such a vast topic that they usually do decompositions and then they pick and choose and do one method of the more advanced approaches. There's also a series of books that are kind of business forecasting textbooks for a complete course beyond what you would get in a business stats book. So I would put our text, the Heinemann book, into that category. I've already talked about Montgomery. I just mentioned this Liefling book. Liefling is a real classic book on marketing models. This book is kind of more advanced. It assumes you already know time series. So after you've done my lectures, then you could go off and read Liefling and it would be good. I've just listed a few other books that are more advanced treatments of this. Okay, so I hope to see you back for the second video.